Hey everyone. Today, we're going to demystify MapReduce, the framework that pretty much changed the game for big data. We're going to see how Google figured out a way to take thousands of regular computers and turn them into one massive data crunching machine. So let's just dive right in. All right, here's our game plan. We're going to break this down into 5 key parts. First, we'll get into what MapReduce even is, like what problem was so huge that it needed this brand new approach. Then we'll look at the programming model, which is actually surprisingly simple. After that, we'll follow a job through the system, see how it deals with failures, which are going to happen, and finally, check out the smart optimizations that make it all run so fast.
So let's start with that big idea. What exactly is MapReduce? And to really get it, you first have to understand the massive scale of the problem it was built to solve.
The goal sounds simple, right? Process data at a massive scale, but it's incredibly tough to pull off. I mean, think about trying to index the entire internet. You can't just buy one giant supercomputer. The only way to do it is to use thousands of normal everyday machines. But here's the catch. You have to just assume some of them are going to fail. MapReduce was designed to hide all of that messy reality from the programmer.
You know, the core ideas here are almost deceptively simple. First, you just chop up the work into tons of little manageable pieces. Then you process all those pieces at the same time. But the real magic is what happens when something breaks. Instead of the whole thing grinding to a halt, you just restart that one tiny piece. And that's the secret sauce. MapReduce creates this layer of abstraction, so the developer doesn't have to worry about all the complicated stuff like machines failing or scheduling tasks. They can just focus on their code.
So, you might be wondering, if the system handles all that hard stuff, what's actually left for the developer to do? Well, that's the beautiful part of this whole model. As the programmer, you really only need to write 2 simple functions, map and reduce. That's it.
Okay, let's look at these 2 functions. On the left, you've got the map function. Its job is to take a piece of data, say a line from a file, and transform it into these little key value pairs. Think of it like putting a label on a piece of data. Then on the right, you have the reduce function. It takes a single key and the entire list of all the values that have that same label, and its job is to merge them all down into a single result.
To make this real, let's use the classic hello world of MapReduce, counting how many times each word appears in a text. So, in the map stage, our function scans the text, and for every single word it sees, it spits out the word as the key and the number 1 as the value. Then comes the magic part the system does for you, the shuffle. It automatically gathers up everything with the same key. Finally, the reduce function takes a word, its now long list of ones, and just adds them all up to get the final count.
Check out this table. It shows you exactly what the data looks like at each stage. Let's follow the word city. So the map function gets the sentence, Waterloo is a cool city, and it outputs the pair city, 1. Now imagine another mapper somewhere else also saw the word city. The shuffle stage, which is happening behind the scenes, gathers them all up, creating the input for the reducer, city, 1, 1. Finally, the reduce function gets that, adds up the ones, and spits out the final answer, city, 2. Simple as that.
Okay, so we've seen the code the programmer writes. Now, let's peel back the curtain and see what the system is actually doing to run that code across a whole data center.
And yeah, that's the real question, isn't it? It's one thing to get the theory of map and reduce, but how do you actually orchestrate all of this in a huge real-world environment?
And here it is. This is the master plan. Now, this diagram might look a little complex at first, but it shows the entire life of a job. Up at the top, you've got the user's program kicking the whole thing off. In the middle, there's a central master. That's kind of like the brain of the operation. And below that, you have all the workers that are doing the actual heavy lifting. We're about to walk through this whole flow step by step. So it all starts when a user submits their job. That's step 1. The master controller then takes these enormous input files and splits them up into, let's say, thousands of smaller chunks, usually around 64 megabytes each. Then, for step 2, it looks around the cluster for idle worker machines and assigns one map task for every single chunk of data.
Okay, now let's zoom in on what just one of those map workers is doing. In step 3, it reads the data chunk it was assigned. It runs your map function, and it holds that output in its memory for a bit. Then, and this is super important for step 4, it writes that intermediate data to files on its own local disk, not some central storage, its own hard drive. This is a huge deal for performance and for handling failures. Finally, it tells the master, hey, I'm done, and here's where my results are.
So now the master acts like a matchmaker. It tells the reduce workers where to go to find all that intermediate data.
For step 5, each reducer reaches out and pulls the data it needs directly from the mapper's local disks. This is that shuffle we talked about, happening in real time. It sorts all that data to group the values by key. And finally, in step 6, it runs your reduce function and writes the final output to a big shared distributed file system, a kind of giant, super resilient hard drive spread across the whole cluster.
You know, one of the most powerful things about MapReduce is that it was designed from day one with the assumption that things are going to break. In a system this big, failure isn't some rare exception, it's just a normal part of life.
And the way it handles failure is just so practical. Okay, so if the master itself fails, well, the whole job is a wash. You got to restart. But if a worker dies while it's in the middle of a task, the master just shrugs and reassigns that task to someone else. Now here's the clever part. If a mapper finishes its job and then that machine dies, you have to redo the task because its output was on its local disk, which is now gone. But if a reducer finishes and its machine dies, we're totally fine. Why? Because its final output was already written to that safe replicated global file system.
It's not always about things just crashing and burning. There's another really common headache in big systems, the straggler. This is a machine that hasn't failed, but for some reason, maybe a bad hard drive or network issues, it's just running way slower than everyone else, and it's holding up the entire job.
And I love this. The solution for stragglers is so elegant. As a job is getting close to the finish line, the master looks at the last few tasks that are still dragging their feet, and for each of them, it launches a backup copy on another idle machine. So now it's a race between the original task and the backup. Whichever one finishes first wins, and the master just kills the other one. This simple trick means one slow machine can't hold the entire job hostage. It's brilliant.
All right, to wrap things up, let's look at a few more clever refinements the system uses to squeeze out every last drop of performance.
There are a few cool optimizations here, but the one I really want to highlight is the combiner. Think of it like a mini reduce that runs right on the mapper machine itself. So for our word count example, instead of sending the 1 over the network 100 times, a combiner could add them up right there on the local machine and just send the 100 one time. This can slash the amount of data that has to get shuffled across the network, which is a massive win.
Okay, this right here, this might be the single most important optimization concept in the whole system. In distributed computing, moving huge amounts of data across the network is always the slow part. It is almost always cheaper to move your little program to where the data already is.
And this is exactly how MapReduce puts that idea into practice. The system is built so that the machines that store the data are the very same machines that run the code. The master is smart. It knows exactly where every single chunk of data is physically located. So whenever it can, it schedules a map task to run on the exact same machine that's already holding that chunk of data. This avoids having to transfer terabytes of data across the data center, which is almost always the biggest bottleneck you'll find.
So look, you might not be writing MapReduce code directly these days, but its DNA is everywhere. It basically proved you could solve gigantic problems using a bunch of cheap, unreliable computers. Which leaves us with a final question to think about. The next time your social media feed instantly refreshes or a search result comes back in milliseconds, think about the legacy of MapReduce. These core ideas, splitting up work, processing in parallel, and just expecting things to fail, they're still powering so much of the world around us. Thanks for watching.